The fine structure constant, often denoted by the Greek letter alpha, is a fundamental physical constant that characterizes the strength of the electromagnetic interaction between elementary charged particles. It is a dimensionless quantity, meaning it has no units and remains the same regardless of the system of units used. The fine structure constant is defined by the formula alpha equals 40 stu, where E is the elementary charge, \epsilon_0 is the vacuum permittivity, \bar h bar is the reduced Planck constant, and c is the speed of light in a vacuum. The value of the fine structure constant is approximately 1/137, or more precisely, 0.0072973525693. This value quantifies the gap in the fine structure of the spectral lines of the hydrogen atom, which was first measured precisely by Michelson and Morley in 18,871. The constant was named by Arnold Sommerfeld in 1916 when he extended the Bohr model of the atom. It plays a crucial role in quantum electrodynamics (QED), the theory of how light and matter interact, and it appears in the formulas that describe the splitting of spectral lines in atoms due to the interaction of their electrons with the electromagnetic field, a phenomenon known as fine structure. The fine structure constant also has profound implications for the universe. If its value were slightly different, the properties of atoms and the underlying structure of matter would change, leading to a very different universe from the one we know. Despite its significance, why the fine structure constant has this particular value is not fully understood, and it remains one of the mysteries of physics. The fine structure constant, alpha, is deeply intertwined with quantum electrodynamics (QED), which is the quantum field theory of the electromagnetic force. In QED, the fine structure constant is the coupling constant that measures the strength of the electromagnetic interaction between charged particles, like electrons and photons. Here's how alpha is related to QED, coupling constant. In QED, alpha is the coupling constant that determines the strength of the interaction between charged particles and the electromagnetic field. The smaller the value of alpha, the weaker the interaction. Feynman diagrams. The fine structure constant appears in the analysis of Feynman diagrams, which are graphical representations of the interactions between particles in QED. Each vertex in a Feynman diagram, where particles interact, involves a factor of the square root of alpha. Perturbation theory. QED uses perturbation theory to make predictions about the behavior of particles. The calculations involve expanding quantities in powers of alpha. Because alpha is much less than 1, this allows for the use of series expansions to make accurate predictions. Renormalization. The value of alpha changes with the energy scale due to the effects of renormalization. At higher energies, the effective strength of the electromagnetic interaction increases, which is reflected in the running of the fine structure constant. Precision tests. The fine structure constant is crucial for precision tests of QED. Comparing the predicted and measured values of quantities that depend on alpha tests the accuracy of QED. The agreement between QED predictions and experimental measurements is one of the most precise in all of science. In summary, the fine structure constant is a cornerstone of QED, affecting the theory's predictions and interpretations. Its precise value is essential for the accurate description of the electromagnetic interactions that govern the behavior of the atomic and subatomic world. The fine structure constant, denoted as alpha, significantly affects the atomic spectra, particularly the spectral lines of hydrogen. Here's how it influences the atomic spectra. Spectral line splitting. The fine structure constant explains the splitting of spectral lines in atomic spectra. When electrons transition between different energy levels in an atom, they emit or absorb light at specific wavelengths, resulting in spectral lines. Some of these lines are observed to be split into several closely spaced lines, known as the fine structure of the spectrum. Energy level shifts. The value of alpha leads to slight shifts in the energy levels of electrons, especially those moving at speeds close to the speed of light. These shifts are due to relativistic effects and the electron spin, which are not accounted for in the non-relativistic Schrödinger equation. The fine structure constant helps in calculating these shifts, which in turn explain the observed fine structure in atomic spectra. Quantum mechanics and electromagnetism. As a fundamental physical constant, alpha characterizes the strength of the electromagnetic interaction between elementary charged particles. This interaction is crucial in determining the energy levels of electrons in atoms and, consequently, the patterns observed in atomic spectra. In essence, the fine structure constant is key to understanding the detailed patterns and structures within the atomic spectra, which are essential for the study of quantum mechanics and electromagnetism. It's fascinating how this dimensionless constant can have such profound effects on the microscopic behavior of matter. Certainly, fine structure in atomic spectra refers to the splitting of spectral lines due to electron spin and relativistic correct ions. Let's explore some examples. Hydrogen fine structure. When examining the familiar red spectral line of the hydrogen spectrum at very high resolution, it is found to be a closely spaced doublet. This splitting is attributed to an interaction between the electron spin, S, and the orbital angular momentum, L, known as the spin-orbit interaction. The straight application of the Schrödinger equation to the hydrogen atom predicts a single line for the red H-alpha line. However, the fine structure reveals a small splitting of about 0.016 nm, corresponding to an energy difference of approximately 0.000045 eV, resulting in an internal magnetic field on the electron of about 0.4 Tesla 1. Sodium D-line doublet. In atoms of alkali metals such as sodium, there are two components of fine structure, called doublets. These doublets arise due to spin-orbit coupling, which accounts for the energy difference between the electron spin being parallel or antiparallel to the electron's orbital moment. The yellow sodium D-line exhibits this fine structure too. Alkaline earth triplets. In atoms of alkaline earths, there are three components of fine structure, called triplets. These triplets result from more complex interactions involving electron spin and relativistic effects. The fine structure splitting relative to the gross structure energies is on the order of Z(2), where Z is the atomic number and alpha is the fine structure constant, approximately 1/1373. In summary, fine structure provides valuable insights into the behavior of electrons within atoms, revealing subtle energy level shifts and spectral line patterns that go beyond the predictions of non-relativistic quantum mechanics. It's a fascinating aspect of atomic physics. Certainly, relativistic correct ions play a crucial role in understanding the fine structure of atomic spectra. Let's delve into the details. Non-relativistic model. The Schrödinger equation, which describes non-relativistic quantum mechanics, provides a good approximation for most atomic systems. However, when dealing with high-precision measurements or heavy elements, relativistic effects become significant. Relativistic kinetic energy correction. The kinetic energy term in the non-relativistic theory is given by T equals 2mp2, where P is the momentum operator and m is the electron mass. In relativistic physics, the total energy of a free particle without potential energy is E equals mc2 plus 2mp2, where c is the speed of light. The kinetic energy in the relativistic case is then T equals emc2 equals 2m1 p2c2 plus m2c4. The first term is the non-relativistic kinetic energy. The second term accounts for relativistic correct ions. The third term is the rest energy. Low momentum expansion. If the momentum is small compared to the rest mass, we can expand the square root in a Taylor series T equals 2mp2c2 plus 2m mc2 2 plus 8m3c2p4 plus. The lowest order perturbation due to relativity is T1 equals 8m3c2p4 application to hydrogen atom. For the hydrogen atom, the energy levels are degenerate, same energy for different quantum numbers, L and m. We can use non-degenerate perturbation theory because we find an operator that commutes with the unperturbed Hamiltonian and the perturbation. The relativistic correction to the energy levels is obtained by applying perturbation theory to the Hamiltonian. Overall impact. The relativistic correction contributes to the fine structure observed in atomic spectra. It accounts for subtle energy shifts and splitting of spectral lines due to electron spin and relativistic effects. In summary, while the Schrödinger equation provides a non-relativistic framework, perturbation theory allows us to incorporate relativistic correct ions and understand the fine details of atomic spectra, especially for systems like hydrogen where relativistic effects are relatively small. Relativistic correct ions play a significant role in the behavior of multi-electron atoms, especially those with heavy nuclei. Let's explore how these correct ions impact the electronic structure. Kinetic energy correct ions. In non-relativistic quantum mechanics, the kinetic energy of an electron is given by the standard expression T equals \frac p2 2m, where p is the momentum and m is the electron mass. However, relativistic effects modify the kinetic energy due to the electron's high velocities. The Dirac equation accounts for these relativistic correct ions. For multi-electron atoms, each electron's kinetic energy is influenced by its relativistic motion, affecting the overall energy levels. Spin-orbit coupling. Spin-orbit coupling arises from the interaction between an electron's spin and its orbital angular momentum. In multi-electron atoms, relativistic effects cause the spin and orbital degrees of freedom to couple. This coupling leads to fine structure splitting in the energy levels. The fine structure observed in atomic spectra results from this coupling, which affects the energy levels of electrons. Briott interaction. The Briott Hamiltonian includes relativistic correct ions beyond the Dirac equation. It accounts for the interaction between electrons' motion and their electromagnetic fields. The Briott interaction introduces additional terms that modify the energy levels, especially for heavy elements. Self-consistent field (SCF) methods. SCF methods, such as the Hartree-Fock approach, incorporate relativistic correct ions self-consistently. These methods iteratively solve the Schrödinger equation, considering both electron-electron interactions and relativistic effects. For multi-electron atoms, SCF calculations provide accurate electronic structure predictions. Negative energy continuum. Relativistic correct ions introduce the concept of a negative energy continuum. Electrons can occupy negative energy states, which affects the overall energy spectrum. The Dirac equation predicts both positive and negative energy solutions, leading to a richer description of atomic behavior. In summary, relativistic correct ions are essential for understanding the electronic structure of multi-electron atoms. They contribute to fine structure, energy shifts, and overall spectral patterns, making them a crucial consideration in atomic physics and quantum chemistry. Relativistic correct ions have a significant impact on the transition probabilities in atoms. These correct ions arise from the effects of relativity on atomic structure and the behavior of electrons. Here's how they affect transition probabilities. Energy level changes. Relativistic effects can alter the energy levels of atomic orbitals, particularly the inner shells. This change in energy levels affects the transition probabilities because the energy difference between levels is directly related to the frequency of the emitted or absorbed photon during a transition. 1. Orbital contraction. Relativistic effects cause the inner electrons to be drawn closer to the nucleus due to the relativistic increase in electron mass. This contraction changes the spatial distribution of the electron cloud, which in turn affects the transition probabilities, as the overlap between the wave functions of different states is altered. 1. Spin-orbit interaction. The inclusion of relativistic correct ions like the mass-velocity correction, the Darwin term, and spin-orbit interaction in the Dirac Hamiltonian leads to changes in the atomic orbitals. These changes influence the selection rules and transition probabilities between different states. 1. Relativistic operators. The effects of relativity on the operators involved in transitions, such as the magnetic interaction and retardation correction in the two-electron operator due to electron-photon coupling, also modify the transition probabilities. 1. In summary, relativistic correct ions are essential for accurate calculations of transition probabilities in atoms, especially for transitions involving tightly bound electrons with high transition energies. These correct ions ensure that theoretical predictions match experimental observations, particularly in heavy elements where relativistic effects are more pronounced. The fine structure constant, denoted as alpha, plays a pivotal role in atomic transitions, influencing the energy levels and transition probabilities of electrons within atoms. Here's a detailed explanation of its role. Energy level splitting. The fine structure constant is responsible for the splitting of energy levels within atoms. This splitting occurs due to the interaction between the electron spin and its orbital angular momentum, known as spin-orbit coupling. The magnitude of this splitting is proportional to 2, making it a key factor in determining the fine structure of atomic spectra. 1. Transition probabilities. The value of alpha affects the probabilities of transitions between different energy levels. In quantum mechanics, the probability of an electron transitioning from one state to another involves the matrix elements of the electromagnetic interaction, which are proportional to alpha. Therefore, alpha directly influences the intensity of spectral lines observed in atomic spectra. 1. Relativistic correct ions. Alpha is also involved in relativistic correct ions to the non-relativistic Schrödinger equation. These correct ions are necessary for high-precision calculations of energy levels and transition probabilities, especially in heavy atoms where electrons move at speeds close to the speed of light. The fine structure constant helps quantify these relativistic effects. 1. Quantum electrodynamics, QED. In the context of QED, alpha is the coupling constant that determines the strength of the interaction between charged particles and photons. It appears in the calculation of Feynman diagrams, which are used to predict the outcomes of quantum processes, including atomic transitions. 1. Fundamental interactions. Beyond atomic physics, alpha is a measure of the electromagnetic force, one of the four fundamental forces of nature. Its value determines how strongly electrons and other charged particles interact with the electromagnetic field, which in turn affects every process involving electromagnetism, including atomic transitions. 1. In summary, the fine structure constant is integral to our understanding of atomic transitions. It influences the energy levels, transition probabilities, and overall behavior of electrons in atoms, making it a cornerstone of both atomic physics and quantum electrodynamics. Certainly, the fine structure constant, alpha, is a fundamental constant that characterizes the strength of the electromagnetic interaction between elementary charged particles. Here are some notable experimental measurements of its value. Castres-Brossel Laboratory, Paris. Researchers at the Castres-Brossel Laboratory in Paris achieved the most precise measurement of alpha to date. They determined the value of the fine structure constant as 1/137.035999206, with an accuracy of 11 digits. This result, published in Nature, provides physicists with a vital tool to verify the consistency of their theoretical models. The fine structure constant is central to the equations of the Standard Model, which predicts and describes fundamental forces other than gravity. 1. Atom interferometry technique. The Paris team used rubidium atoms in a technique called atom interferometry. By continuously improving their apparatus, reducing noise, and addressing systematic effects, they achieved a measurement that is 3 times more accurate than the previous record. The previous record was set by a team from the University of California, Berkeley, using cesium atoms. 1. Binding energy of hydrogen atom. The fine structure constant is crucial for calculating the magnetic moment of the electron. Using alpha in the Standard Model equations, physicists can predict the magnetic moment of the electron with high precision. The agreement between predicted and experimental values for the electron's magnetic moment provides an outstanding consistency check of the Standard Model, particularly its electromagnetic sector. 1. Anomaly of the electron's magnetic moment. The fine structure constant also explains the subtle anomaly in the electron's magnetic moment. The measured magnetic moment is slightly larger than expected for a charged, point-like particle due to relativistic effects. This anomaly has been verified with increasing accuracy and is considered one of the Standard Model's greatest triumphs. 2. In summary, these precise measurements of alpha contribute to our understanding of fundamental physics and provide stringent tests for theoretical models. The fine structure constant continues to be a cornerstone in our exploration of the universe's building blocks. The fine structure constant, alpha, is crucial in the Standard Model of particle physics as it affects the behavior of other particles through the electromagnetic force. Here's how alpha influences various aspects of particle behavior. Electromagnetic force. Alpha characterizes the strength of the electromagnetic interaction between charged particles. It determines how strongly particles like electrons, protons, and charged bosons, W and Z particles, interact with photons, the carriers of the electromagnetic force. 1. Quantum electrodynamics, QED. In QED, which is the part of the Standard Model that describes the electromagnetic interactions, alpha is the coupling constant. It appears in the calculations of the probabilities of various processes, such as particle scattering and decay rates. 1. Anomalies. The fine structure constant is involved in the precise calculations of anomalies, such as the anomalous magnetic moment of the electron. This quantity is subtly larger than expected for a charged, point-like particle by a factor of roughly 1 plus \frac alpha 2 pi. The anomaly has been verified to ever-increasing accuracy, becoming one of the Standard Model's greatest triumphs. 1. Particle masses. The value of alpha is used to calculate the masses of particles. For example, the binding energy of a hydrogen atom is about \frac alpha 2 times the energy associated with an electron's mass. This relationship is essential for determining the mass of the electron. 1. Standard Model tests. Precise measurements of alpha provide stringent tests of the Standard Model. Any deviation from the expected value of alpha could indicate new physics beyond the Standard Model, such as the existence of speculative particles. 1. Running of alpha. In the Standard Model, alpha is not a constant but runs with energy due to the effects of virtual particles. At higher energies, the effective strength of the electromagnetic interaction increases. This running of alpha is a prediction of the Standard Model and is confirmed by experiment 1. In summary, alpha is integral to the Standard Model, affecting how particles behave, interact, and how their fundamental properties are calculated. Its precise value is essential for confirming the accuracy of the Standard Model and for exploring potential new physics beyond it. That was all. Goodbye.